Good afternoon, everybody. Welcome to another exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Now, let me remind you, right after class today, and I think I'll be going till 2:15 or 2:30, maybe 5 o'clock, no, but probably an hour and a half, maybe 2 hours, because I want to finish some stuff. We'll I'll be sending out the email with the password for test number 3, which is located in the assignment area of T2L. You have until tomorrow, either 10 or noon, to get it back to me as a single PDF file. Remember, you should not be looking at your notes. That's cheating. And I have secret things put in my test to know if somebody does that. Dr. White's a power computer user, so look out. But anyways, I will be checking my email frequently this afternoon, this evening, and tomorrow morning. If you have any questions about tests, always feel free to email me. Also tonight, I'll have my office hours, so if you have any questions about the test, stop by. With that, it's time to get going. Now, on Monday, we got heavily into fats and oils. And I talked about hydrolysis, and let's do one. Hopefully you all can see the whiteboard. And one of the things I said for this class, if I say tallow, which you should know is beef fat, yellow grease, which is pig's fat, what type, quality of it, that's, or white grease, that's a better quality of pig's fat. You pay about a penny or two more a pound. If you're buying 100 million pounds, that's a lot of money. You should use the following. Where S means this will form stearic acid when it's hydrolyzed. O means this will form oleic acid. Now, in real life, there's about a 50-50 mixture of stearic and oleic in tallow, yellow grease, white grease. But how can you show on a simple molecule 50-50 when there are three of them? You can't. So this is a good approximation. I could have put OSO or OSS, but SOS is Dr. White's little joke, save our ship. Now, we talked about the fact that these are esters, and I taught you on Monday that one way of making a reaction go faster is to catalyze it, like with acid or base. Another one is to increase the temperature. In this case, we use high pressure steam. Remember, steam is hot water, very hot water. And what this is the same as acid hydrolysis, except you use steam instead of acid. You get back the alcohol plus the carboxylic acid you would have used to make that ester. And therefore, I'm going to make you work from the start. What would be the product or products, organic products, for this reaction? Ready, set, go. Oh, while you're here, Paige, uh, your question a couple of days ago by email about grading the labs. If you look at T2L uh, grade book or whatever they call it, uh, your grades, you should see I'm up to date, except what you handed in today.
I did see that. Thank you very much.
You're welcome. Uh, my back problems caused me to, how should I say, be off schedule and be late on things which I normally am not. And again, I normally don't spend 3 weeks, 3.5 weeks sleeping in my lazy boy because I can't get out of my bed when I get in there without having fun with serious pain. It's not fun. But anyways, things are getting better. I'm catching up. All right, anybody need more time? All right, let's do this. What do we have? 3 esters. Remember, identify what's different in a molecule. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention. So if I look at the first ester, I will get this alcohol plus this carboxylic acid, which is a fatty acid, comes from fats and oil, stearic acid. This ester, I will get this alcohol plus what's the R group, RSO. I'll get oleic acid. And finally, hi Alondra, my regulars are back. The final ester, I get this. Now I'm done. What? What do you mean you're done? The problem asked, as I've done all semester, give the organic products for it. And what you get is glycerin, stearic acid, but you get 2 of them, one from this ester and one from this one, but they're both the same thing, stearic acid. So if you want to write it a second time, you can. I'll do this. This is going to be real rare. Put this down in your diary. Dear diary, Dr. White, balance the chemical equation. Oops, that should be an S. Now this right here, you don't have to, and this don't, because what you get is glycerin, stearic acid, and oleic acid. So for this reaction, you get 3 products. Even though I'm not balancing it, you get 2 of these the way I have it written. In real life, you get about a 50-50 mixture of oleic and stearic. How do I know that? Because I work for a company that does this reaction to the tune of about 2 to 3 million pounds a week. Ooh, do I have time? I do. It's time for Dr. White to ruin your life. No, not really, but for those of you who use personal care products like shampoo, soap, certain, not the liquid soap, but the bar soap, and also hair conditioner, certain types of makeup. If you look at the label and you see something like stearate, oleate, palmitate, or similar type names, guess where the raw materials come from in those products? Beef fat and pig's fat. Yep, but you're not putting that on your skin or hair because by then it's been converted into other chemicals. How do I know? I've worked with those chemicals. I've worked at those companies. By the way, your fabric softener comes from pig's fat and beef fat too. Now, I really ruined your day. But by the time it's on the dryer sheet or the liquid you put into your washing machine, it's no longer beef fat or pig's fat. By the way, I didn't tell you the other day when I was talking about it, seriously, tallow, beef fat, yellow grease, and white grease, which is pig's fat, is a very important industrial chemical in the United States, if not worldwide. And many contracts for chemicals say I'm company A and company B buys from me a product that somewhere before was made from tallow or yellow grease, white grease. The contract price is written, so it's some formula that includes the price, current price of tallow or beef, yellow grease or white grease. And guess where you can find that? One is a magazine you don't know about called the Chemical Marketing Reporter, which comes out weekly. And when I worked at two companies, it would be circulated in the company through a few people. They got a couple issues, and I was always on that circulation list. The other place, which you wouldn't realize, but it's there every Friday, if you know where to look, in the Wall Street Journal, they have the price of tallow, white grease, and yellow grease. FOB New York, I think it is, or maybe Midwest. FOB is freight on board if you were to buy it in that location where you're not paying extra freight to ship it to you. And contracts are actually written based on the price of either the Chemical Marketing Reporter, CMR, or Wall Street Journal. That's how important yellow grease, white grease, and tallow is. And you're talking to someone who worked in the industry. Aren't you lucky all these neat things? Now you can gross out your friends, neighbors, and loved ones saying, do you use skin conditioner? If you look at the label, most of that comes from beef fat or pig's fat. Nah, don't do that. You'll lose a friend real quick or loved one. All right, let's continue on. Now, saponification is a reaction we went through for test number 3. You should know, hint, hint. But let's take a look at it with fats and oils. And what is saponification of an ester? And I'll write the ester how an oil chemist would write it. And usually it's sodium hydroxide and water. Usually I have to heat this up a little too, but I haven't really gone into reaction conditions. And what you get back is the alcohol you would have used to make this ester, plus not the carboxylic acid. Because you're in base, the carboxylic acid you would have used to make that ester forms the carboxylate anion. So I'm going to do a real hard one on you. Give the organic product or products for the following. Now, time for a little hint and help from Dr. White. Hint, hint. Everybody get the hint? Your turn. And you get 3 products, 3 distinct different molecules. I was just looking at the calendar this morning. Thanksgiving's not that far away. Oh my goodness, where did this semester go? Oh, if you know anybody you don't like, let them know they should register for my spring Chem 170 course. Dr. White's being facetious, but by now you know I do that once in a while. I already have 4 people signed up in the first day. So if you know anybody who needs it, it'll be totally online like this one. And I'll do the same thing, post my videos. Boy, I'm going to have tons of videos on YouTube now. And when you're done, give me a thumbs up or smile broadly. or you can give me the high sign. All right, looks like everybody's done. How do you do this? What is tallow? For this class, I'm using this designation or molecule. And we're reacting it as it's with sodium hydroxide and water. So we have 3 esters. Ooh, ester number 1, 2, 3. Now, ester 1, when you react it, and here's the general reaction. Think about how much you know now that 6 months ago, do you know what I was talking about or where to look? You should be proud of yourself. All right, first ester gives me this alcohol, plus now this carboxylate anion, where our group on the carbonyl is R sub S. Ester number 2 gives me this alcohol, plus this carboxylate anion, where here's the R group on the carbonyl. And finally, the last ester, ester number 3, gives me this alcohol. However, this will be sodium stearate, and I've already written it. Now, if you want to write it again, you can, or if you want to put a 2 there, you can, but you don't have to, because the question asks, give the organic product or products, and you get glycerin, sodium stearate, and sodium oleate. And that's how you do it. Now, why is this called saponification? Because later today, I'll teach you that these molecules we call soap. If you have bar soap in your bathroom, that's what it is, a mixture of these 2 chemicals. And we used to make this, or I used to make, interesting sideline. These are solids at room temperature. And we had machines that made them into little pellets. And I don't know how it got this name that, but they were called soup noodles. You wouldn't want to eat them, but they didn't look like noodles, but they were called soap noodles in the industry. And people would buy them, or they'd buy the carboxylic acids to make their own, reacting it with base. A lot of companies bought their own carboxylic acids, but all your bar soaps are sodium carboxylates of fatty acids, mainly stearic and oleic acid. See, I told you, a lot of stuff you use comes from fats and oils. Now, let's talk about hydrogenation. And this is the reaction of a fat or oil with hydrogen gas and a catalyst, which you learned about in the past. Let's do a little quick review. Double bond reacting with hydrogen and a catalyst, and the catalyst can be nickel, platinum, or palladium. Remember, this is made up of a pi bond. That's an awful looking pi. Hold on. That's better. Pi bond and a sigma bond, single bond. You don't break single bonds, of pi bonds you can break. And each carbon of the double bond gets a hydrogen. Well, let's look at the following. Now, if I took this molecule, which is oleic acid, and reacted with hydrogen and catalyst, nickel catalyst, what would you get? Let me give you a heads up, and this is the beauty of synthetic organic chemistry. There's no reaction I know of where carboxylic acid reacts with hydrogen and a catalyst. It doesn't. So why don't you try, see if you can write the structure for that or the product. If you haven't figured out, my back is better, so Dr. White's doing a lot better today. For a while, if you had pain level from 0 to 10, when I was getting out of bed, I was at a pain level about 15. All right, when you're done, give me a thumbs up. All right, I think everybody's done. So let's take a look at this. What do we see that's different? Well, we got the carbonyl and the hydroxycarboxylic acid, but that won't react with hydrogen catalyst. But, oh, I've got a double bond. Do you break carbon-carbon single bonds? No. So, now the pi bond, I'll break, and each carbon gets a hydrogen. And then I get this molecule. Now, I'm going to rewrite it. And let's take a look at this. I have a CH3. Now I have 7 CH2s, but here's a CH2, here's a CH2, plus 7 more. So 7 plus 7 is 14, plus 2 more is 16. And then I have my carboxylic acid, and these are the same molecules. And what is this? You should know that's stearic acid. So if you take oleic acid, hydrogenate it, you get stearic acid. Oh, let's do another one. And here's one for you. You take this molecule and hydrogenate it, what do you get? I'll wait until you're all done so I don't give away the surprise ending. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's take a look at this. Well, what's this, R sub O? Well, this is R sub O. And what do we get? We get stearic acid. And how do you show stearic acid? When I give you an abbreviation, you don't have to write it out. You can write this out. And really, these are the same reactions. I'm just using this abbreviation. So the double bond is lost and the O becomes an S. Well, let's talk about hydrogenation of fats and oils. What if we take tallow, which is quite inexpensive, or white grease or yellow grease, and react it with hydrogen and a catalyst like nickel? So you've seen my designation for tallow. And why don't you do this one? Your turn. Wow, I'm really being nice today. I'm doing a lot of sharing. All the fun. And when you're done, give me a thumbs up. I think everybody's done. So let's take a look at this. Well, this is an ester. Esters do not react with hydrogen or with a catalyst. So since it doesn't react and it doesn't break carbon-carbon single bonds, now what's R sub S? Well, if we come up here, that's this right here. This carbon-carbon single bonds. Does that react with hydrogen and catalyst? No. So that means I'll still have this. I'll still have this. The only one here, R sub O, what is that? Well, that's this, which becomes this, which you learned R sub O becomes R sub S. And therefore, there's the answer. Now, why would you do this? Well, let's look instead of tallow. Let's say we have some vegetable oil, which is cheaper or cheap compared to other chemicals and is easily obtained, or even corn oil. And vegetable oil is highly unsaturated, double bonds like this. They're more R sub O's than R sub S. And if I react this with hydrogen and a catalyst, why nickel? Because in industry it's cheaper than platinum or palladium. You can't get away, the cost would be prohibitive. What happens? Well, the ester function is not reacted. And R sub O becomes R sub S. Same thing here. And you get this compound. Now the question is, so what? Why do you get that compound? Well, it's time for Dr. White to tell you some things about the facts of life concerning hydrogenated fats and oils. Hydrogenated means add hydrogen to catalyst. Well, when you have a vegetable oil, oil means it's a liquid at room temperature. When you hydrogenate it or partially hydrogenate it, it becomes a solid or semi-solid. So what? Well, if I take that solid and mix it with some food coloring like yellow and some flavorings, artificial flavorings like butter flavoring, we have margarine. And margarine is mainly, for a long time, they've changed some things recently, but was hydrogenated vegetable oil mixed with water, which is cheap, and also flavoring and food color. And for that, I can sell you a tub of that for a couple of bucks, a couple of dollars, let's not use slang, and I could make a lot of money, even though it's going to be bad for your heart, because hydrogenated fats and oils, medical science tells you is bad for your heart. But guess what? The margarine companies don't care. They're making money. It's not the only thing, companies that feel that way about consumers, but that's another course. Now, when I was working at Unichema, we were part, at that point, that company was part of Unilever. Unilever, also known as Lever Brothers, but Unilever is huge conglomerate. And once a year, all the senior managers would meet, research managers and also marketing managers and other people. Some of us key people would meet for a conference in a very nice location. This year I'll tell you the story, was in upper New York State at this beautiful resort that had these beautiful cabins that were more like suites. We each had huge bedrooms. They had, each bedroom had its own bathroom. There were four, I don't know if you really call them cabin suites. And then they had a dining room. It was like going to a cruise ship. You paid for nothing and all drinks were free. It was dangerous. Well, first day, and there are about 100 of us there. We're all together in this meeting room, senior vice president giving a talk. One of the reasons we had this was to promote interdisciplinary friendships, that if somebody had a problem, they knew they could call you. Oh, that guy works in this area. Maybe he can help us out. And that was a key reason for doing that, quite important reason. Well, anyways, this is back in 86 or 87, 1986 or 87. And this was before cell phones. Yes, there was a time before cell phones. And this was a time before the internet. Yes, there was a time before the internet. Well, anyways, about an hour into the, not even that long into the meeting, it was all morning meeting with talks, the owner of the resort comes in, can so-and-so please come, there's an important phone call. And the guy gets out, turned out he was the marketing manager. And he comes back 10 minutes later, owner comes in again, can so-and-so come, there's an important phone call. He goes, comes back, 15 minutes later, fourth time, the person in charge of the whole conference, the senior vice president for Unilever, said, I think you better go back to your office in New York because you're needed there, instead of being called to the phone every 15 minutes, which he did. Well, having contacts like I have, I found out what was the story behind there. Well, it turns out that gentleman was the senior marketing person in charge of the rollout for the first time throughout the whole United States of a new Unilever product called, I can't believe it's butter. I think you've heard of that product. And it's a margarine. And they had made something like a couple 100,000 cases, 24 in a case, to ship to the whole United States to have the national rollout of this new product and make a lot of money for the company. Well, somebody opened up a case and opened up some of it, and they took out the package or the container, took the lid off, and there's like aluminum foil or covering on it, and it was bulging. And it shouldn't be bulging. And if you bought a product, what's wrong with the product? I want my money back. So that was the problem. I never found out what caused it. It was nothing lethal. But the way they solved it, because they had a couple 100,000 units, they hired some high school students with very small syringe needles and popped it, pushed, got the air out, and sold it. And nobody got sick, but true story. So next time you see hydrogenated fats or oils on a product, you know they took vegetable oil, reacted with hydrogen and a catalyst to get rid of the double bond, so it makes it semi-solid or solid, and they can pass it off as butter. For those of you who like super buttery microwave popcorn, they use hydrogenated vegetable oils. Oh gosh, you know something? I forgot to teach you something real quick. How many of you have ever had microwave popcorn? I stay away from it now. I make my own air pop with an air popper in my microwave. But anyways, um, after they'd been making that a while, a number of the workers were getting sick, seriously sick, with a lung disease. And it got so bad that disease was called popcorn workers' lung disease. And turned out the chemical that they put in the microwave popcorn to make it taste buttery, along with the hydrogenated fats and oils, or actually oils, was causing that, and they changed to a different one. But that chemical, this won't be on a test or anywhere. Just remembered I never taught you that. It's got a common name of diacetone. And this is a chemical. They've changed it. I think they added an extra carbon. I wouldn't. And but this gave it, for some reason, this makes your brain, from your tongue to your brain, say, "Ooh, that tastes like butter." How? I have no idea. But if you ever want to look up popcorn lung disease, now, funny story. That's not that funny, but after this been in the news and all that, some lawyer sued the companies that made the microwave popcorn because he claimed, oh, I have popcorn workers' lung disease. Why? Because he was eating about 8 or 10 bags of popcorn per day, he was claiming. Yeah, right. I think it got thrown out, at least I hope it did. And let's do one more reaction. If you had a hot dog or hamburger today, or if you had bacon this morning, or I could also write yellow grease or white grease. And you chewed your food before you swallowed it, and it went in your stomach. And what's in your stomach? Acid and water. What would be the products of the following reaction? I'll let you try that. Oh, I'll help you out. Hopefully you know this for test number 3. All right, fess up. Which one of you snuck into my office just now and changed the clock? I just started and it's already 1:40. Actually 1:41. Boy, this time flies when you're having fun with organic chemistry. Bet you didn't realize how much fun it is. If I say that enough times, you'll believe me. And when you're done, give me a thumbs up. All right, looks like everybody's done. How do we write tallow, white grease, or yellow grease? Isn't it amazing the molecules Mother Nature created? And as I keep on telling you, the best organic chemist around is Mother Nature. And once again, we have ester number 1, ester number 2, and ester number 3. And if we look at ester number 1 and this general reaction, what do we get? The alcohol you would have used to make that ester, plus this carboxylic acid or fatty acid, stearic acid. Then ester number 2, you'll get this alcohol. Notice what the R prime is, and you'll get oleic acid. And finally, ester number 3 will get this alcohol. And so overall, you get glycerin. And this right here becomes stearic acid. If you want to write it again or put a 2 there, it's cute. Some semesters when I do this, I see on the test, and this is test number 4 material, students actually write this, and they write it tiny like I do with the quotes. I always get a good big kick out of that and laugh. So you get glycerin, stearic acid, and oleic acid. And why is this important? Because this is how your body breaks down fats and oils. And one of the things I mentioned Monday, that you should know how to describe what happens when you eat anything with fat or oil in it. So if you eat anything with a fat or oil, you need to know how to describe with a general reaction what happens in your stomach and by words. Words is acid, hydrolysis, of an ester. And the general reaction, I'll write it like I have all semester, like a synthetic organic chemist. You have an ester, you get back the carboxylic acid plus the alcohol you would have used to make that. So next time you eat anything with fats or oils or butter on it, which contains fat, and if you eat anything with oil in it, like mayonnaise, hot dog, hamburger, other things, if you have oil vinaigrette dressing, in your stomach, what goes on, I think it's small intestine, you have acid hydrolysis of an ester, and here's the general reaction. But you didn't know you were a walking chemical plant, and a lot of things are going on in your body that are organic chemistry. Before we take a break, I'd like you, if you have a chance, to tell me or send me an email how you, and this has nothing to do with your grade or anything, and I won't, do you feel the way I'm presenting this course online gives you a similar feel for how you, if you were in a classroom, is the same, better, or worse? And the reason I'm asking is yesterday, one of the book companies, which I get asked to on times, has various meetings where they invite various faculty from around the United States to talk about their experience, especially now with the virus, and look at some new concepts they're trying to develop and what we think of that. And I had one yesterday with a major book publisher who has some really good titles. And it was interesting. One of the instructors from, I think she was from Louisiana, I forgot what college, said that all of her students felt that in-class lecture was much better than online. They really didn't like online. And I asked that faculty member, are you talking about a totally asynchronous, where here you just learn it on your own and I'll be by for any questions? Or like what I'm doing, which is actually giving lectures, even though I have made it asynchronous because I posted in YouTube, but for real, it's like on like a regular class. And I was just wondering, I have my thoughts on it. If you want, send me an email if you feel this is similar and has nothing to do with your grade, never will. I'd say send it anonymous, but I don't have an anonymous Dropbox. Maybe I could create one, but if you give me some feedback, I'd appreciate that, because I know from my general chemistry, they feel providing, meeting the needs similar to what they would in class. All right, let's take a look at it. Know something? Let's take an extra long break. We'll come back, finish some stuff. We'll do the lab. I'll get you out of here before midnight. And with that, I'll see you at 1:55. 1:55. That's when the big hand is on 11. For those who have digital watches, 1:55. I'll see you in a little while. I'm going to go stretch. time to come back. All right, let's continue on. And now I'm going to get into something very important. Now we did hydrogenation. So now it's time for you people to get clean. How? I'm going to teach you how soap works. I think you're all familiar with the soap you use to wash your hands, your hair, your face. Your detergent works similar for your clothes. Your dishwashing soap. How does soap work? By the way, switch is on for this big time. Now, there are a series of molecules called surface active agents, but organic chemists are lazy, and this is abbreviated by the term surfactants. And I worked for 2 companies that made surfactants. And this is an area of expertise for Dr. White. And soap is a surfactant. Now, what does that mean? Soap has a hydrophilic tail, also known as lipophilic, hydrocarbon tail, lipophilic, and a polar head, hydrophilic. Now, lipo means fat or carbon. Hydro means water or polar. And, oh, I left a note for myself. Remember, like dissolves like. Well, now I have to teach you a very important, useful concept, and that's like dissolves like. Now, what is like dissolve like? It's a rule of thumb. See, it's on this way. It's on this thumb. Now, what's a rule of thumb? A rule of thumb is something that's true about 90–95% of the time, most of the time. Now, it's not a law, because something that's a law is always true. Well, a rule of thumb, there are exceptions. But for the most part, it is mostly, like almost always, true. Now, when we talk about like dissolve like, what that means is polar substances are soluble in other polar substances, or sometimes solvents. But oh, by the way, if I spell anything wrong, let me know. I was always the first one down in spelling bee. So polar substances are soluble, and that's the key thing, soluble in other polar substances. And nonpolar substances are soluble. I wish my tablet had a cut and paste, but it doesn't. Ooh, forgot an R up here. Don't forget to put it in other. Like dissolve like. Polar substances are soluble in other polar substances, and nonpolar substances are soluble in other nonpolar substances. If you take something that's polar, mix it with something that's nonpolar, it's not soluble. You get a heterogeneous mixture, 2 layers, it's not the same. and that's like dissolves like. Now, what are important polar things you should know? The most polar thing in our universe is water. Alcohols are polar. That's why you can make a mixed drink. By the way, bartenders don't like being told, you know how you can make it, why you make mixed drinks? Because ethanol is soluble in water because the like dissolves like. They don't like hearing that. And finally, any salts, most salts like sodium chloride are polar. Now let's look at things that are non-polar. Well, one of them is vegetable oil. And if you've ever made an oil vinaigrette dressing, you shake it up, you put it on your salad, and after a couple minutes when you put the bottle or container down, what happens? It separates. The bottom is the oil vinaigrette. Remember, vinegar is mainly water with a little acetic acid. And on top, you have vegetable oil. Polar, non-polar, they're not soluble. What are some other things? Well, baby oil is non-polar. That's why it's used on a baby to keep moisture off. And what's another one? Vaseline. And finally, two important ones, dirt. You don't think of dirt as a chemical or chemicals, but it's non-polar, and so is grease. So if you get grease or dirt on you, on your clothes, water won't take it off because they're non-polar. And like dissolves like tells you these things are not soluble in water because water is polar. So what do? Because if you go and work outside, oh, look, I got dirty hands, and you put it underneath the water, they're still dirty. What do? You use soap. Oh, before I do this, I'm going to be teaching you how soap works. If I could turn a dial that goes from 0 to 10, I've just turned it all the way to 100. You should know the following. How does soap work? And the following thing I'm going to teach you, you should know. Soap and detergents are the same way. As a non-polar tail, and these are like CH2, 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 CH3 at the end, and a polar head. You should know this. Now, let's take our magnifying glass out or microscope. And here I have a little piece of dirt that happens to be on my hand, and I've blown it up. Now, if you take water and mix it with dirt, water says to dirt, you're non-polar, I'm polar, I know like dissolves like, I want no part of you. Now, if you take water and soap and mix it and rub your hands together with it, notice the non-polar part, the tail of soap is non-polar, dirt is non-polar, and it goes like this. This non-polar tail is attracted to dirt because the like dissolves like. And the polar head wants to stay as far away from dirt. And that's the interesting thing about all surfactants. Most of them have one side that's non-polar and another side that's polar. And therefore they can interact with other things that are polar and non-polar. Well, it turns out you got more than one molecule of soap. I'm just going to throw a few in. And this totally surrounds the dirt molecule. And what this is called when the dirt or whatever particle is surrounded by the soap, this is called a micelle. And you should know the structure of a micelle. How many of you heard of the product? And a couple of years ago, one Chem 70 student brought in an ad from one of her magazines called Micellular Water. Have you ever heard of that product? It's a cleansing product. And it's a good product. At least my students tell me I don't use it. But guess what? It's misnamed. There's no micelles in the water that you in the bottle you buy. It's soap and other chemicals that once you interact that with your face, cleaning off makeup and whatever, then you're forming micelles. Now, if you had bought the book, which hopefully you didn't, so you save money, you would see this pretty picture right here. Can everybody see the blue spheres? And if you cut out a piece, assuming this is surrounded like a orange or whatever round, if I were to cut out a section, look inside, in the very center, hold on one sec. Let's work on here. Look out. In the very center here, I have my dirt. And then all around this, you see the non-polar heads, tails here, and on the outside, the polar heads. So once you form a micelle, and each one of these are a micelle. By the way, if I were in a bad mood, I'd say, no, not your cell, it's my cell. Is that awful joke or what? But anyways, the micelles are formed around all the dirt particles. So now if we go back to my outstanding drawing here, now when you have a micelle, water looks at the micelle and says, oh, I'm polar, and all it sees is the outside polar heads of the micelle. You're polar, let's go down the drain together. And they do, and now your hands are clean. By the way, you form different, similar type of micelles when you're washing your hair, when you're washing your clothes, and when you're washing your plates or cleaning up after dinner. You're forming micelles, and that helps the non-polar things go down the drain. All right, let's go through this. You should know the following. Get the picture? All right, this is what you should know. First of all, you should know what is the structure of soap. It's a non-polar tail and a polar head, and how to draw it like this. Next, you should know light dissolves light. In the key picture, the most important thing how soap works is light dissolves light. This is the key to the puzzle. If we were in a classroom at ECC, I'd be writing this on a board, and each letter would be at least a foot high, because this is how important it is. Now, the soap has a polar head and a non-polar tail. And dirt is, oh, it says it right here, non-polar, and water is polar. So how do you get two to mix together? With the soap, the nonpolar tail is attracted to nonpolar dirt. And the polar heads are on the outside, and you should know this forms the micelle. And you should know how to draw a micelle. And now water looks at the micelle and says, oh, look, I'm polar, you're polar. I know and you know light dissolves light. That's the important part of the puzzle. And therefore, let's go down the drain together. And the next time you wash your hands, did you realize you're doing serious organic chemistry? You are. Ooh, something I haven't really done much this semester, but I'm going to do it now. It's time for Dr. White's show and tell. Usually I bring a whole, this one bar. This is my favorite soap. I don't like liquid soap for a shower. And this is Dial. I love that perfume. Can everybody see the label there? No. So let's look at a better one. By the way, bar soap. This is organic chemistry. Surprise, surprise. Can everybody see the label on the right part of the screen? You see that all right? And it says ingredients. And the first one it says is soap. And if you look in there, it says sodium cocoate, sodium palmkernelate, sodium palmitate, and sodium tallowate. What is that? Those are all fatty acids. It's mainly sodium tallowate. What is tallowate? It's a mixture of stearic and oleic acid and other fatty acids coming from beef fat. So Dial soap I'm using originally came from beef fat. Now, it also has water, talc. Now, they put in to protect themselves coconut acid, which really makes sodium cocoate. That's C12, C10 chain length. And sodium palmitate is 16, which is also a little in tallow. And palm acid, tallow acid, and palm kernel acid. I forgot what vegetable oil that is. Now, see where it says PEG 6 methyl ether? Everybody see that? That's methanol ethoxylated with 6 moles of ethylene oxide. You know that reaction. You did that for test 2. And why did they put that in there? Well, that helps keep if they have a fragrance and a dye in the bar and mixed together. And notice you have a fragrance, there's some glycerin. Sorbitol, I have no idea. Sorbitol is a sweetener, and luckily my mother never washed my mouth out with soap. She did other things to let me know she was upset with me, but luckily that wasn't. How many of you seen the movie A Christmas Story with Ralphie? I actually saw it the first time I was in the theater. I still love that movie. By the way, I had a BB gun too. And no, I never shot my eye out. I was more careful, but sodium chloride is put in there to viscosity modifier when they make the soap, and pentasodium pentanate, and the next one are preservatives, the different colors. Now this one has these colors. Sometimes you'll see titanium dioxide, which is usually for a white color. I'm surprised they don't have that here. But the key thing here is it's a carboxylate anion of a fatty acid. And what sodium tallowate is, now let me go get some clean surface here. Sodium tallowate is a mixture of these two carboxylate anions. If I write, say, stearic acid out, or sodium stearate, really, and this is a major part of bar soap, this part is your nonpolar tail. Hydrocarbons, carbon and hydrogen are nonpolar. And see how this has a charge to it? This is your polar head. And this morning when I was taking a shower and using a soap, I was probably the only one in the city where I live thinking, oh, look, I'm making micelles. I was. Now you know Dr. White's an organic chemist, industrial organic chemist. And I worked for a company that made this or the precursor tallow acids, sodium and stearic acid and oleic acid. And that's soap. It's not magic, it's organic chemistry. But let me go through this again because this is so important. There are a few things I'd like you to leave this semester knowing. And one of those is how soap works. Now, the most important thing to remember when you're how does soap work is like dissolves like. And next week we'll do a lab with like dissolves like. And polar substances are soluble in other polar substances. Non-polar substances are soluble in other non-polar substances. You mix polar and non-polar, they're not soluble. Well, if we look at what's polar, water, alcohols, salt. What's non-polar? Vegetable oil, baby oil, Vaseline, and the most important thing, dirt and grease. And also motor oil is non-polar. Anyways, you should know what's the structure of soap. Non-polar tail, polar head. Dirt, non-polar. It won't attract water because the light dissolves light. The whole important piece of the puzzle is light dissolves light. Let me do something and press it even more importantly. The most important thing of how soap works and because the light dissolves light, the nonpolar tail of soap is attracted to dirt. The polar head stays far away and you form a micelle. You should know how to draw a micelle. And now water sees the micelle and only sees the outer polar heads of the soap and says, oh, micelle, I'm polar, you're polar, let's go down the drain together. And they do, and now you're clean. And that's how soap works. And here's another look at micelles with a fancier picture. Now, I'm going to turn the switch off here, but your synthetic soaps, like your liquid soaps or your detergents, are linear alkyl benzene sulfonates. I'm turning the switch off on this, but in case you were wondering, for liquid soaps, if you use liquid soap in your bathroom, and this is usually about a C10 or C12, here you have your nonpolar tail. Again, switches off for this. And this part is your polar head. And just like bar soap, like dissolves like, that's how it gets your body clean, your hair. Now, detergents are a little different. And from World War II, and here is 9 to 12 carbons. And this part here, long R group in a benzene ring, is nonpolar. Tail. This part is a sulfonic acid group that's been reacted with base, and this is your polar head. And the next time you do your laundry, think about it. In your laundry machine, your detergent is making micelles on the dirt on your clothing, and the micelles say to water, hey, I'm polar, you're polar, let's go down the drain together. And that's how you get your clothes clean. Now, quick little story, and then it's time for us to go to lab. Years ago, I was sitting watching TV, and they were doing this commercial for, I forgot what detergent, laundry detergent, and they were saying, it's so good, it cleans greasy dirt. I started laughing. Greasy dirt, got grease, got dirt. I guess if you mix them together, you have greasy dirt. So if you ever happen to have dirt on your clothes and you slap some grease on there, you'll get greasy dirt. But that was funny. All right, first of all, time for don't forget, that's organic chemistry. And oh, I love the smell of the spring water scent they put in there. But remember, this comes from beef fat and pig's fat. Now that I've ruined your day, let's do something else. Let's do the lab. It's time for the lab. Today's lab deals with polymers, and I'm sad. Why? Because it's such a fun lab for you guys to do. I wish you were in the lab to do this, but tough times, unfortunately. I had a choice. I could have had you come in for a couple labs, but I don't think to expose you possible danger at ECC, and me too, was worth it. So I created our own labs. All right, everybody see the lab, polymers, Chem 170? I assume you can. Now, polymers are macromolecules that come from monomers that are hooked together like boxcars. Now, there are different types of polymers. One is polyurethane, and a polyurethane polymer these are functional groups that I didn't teach you in the classroom. This is called an isocyanate. React it with why did that go super large on me, that plus sign? I have, hold on. Hang in there, I just lost my, I don't know why it's playing games with me. There we go. Well, anyways, you have an isocyanate reacting with an alcohol, and this is like a carboxylic acid, but more reactive, and you form this is called the urethane. Now, if you have an isocyanate with more than one molecule with more than one isocyanate. We call it a polymer isocyanate. And we have an alcohol with molecule with more than one hydroxyl group, alcohol. We call that poly, many, all, alcohol, polyol. You form a polymer. Now, all right, this is weird. Hang on. Let me close some things up. All right, let's try it again. And you form a polymer. Now, interesting thing, you can form a foam with this by adding what's called a blowing agent. And let me check something. A blowing agent, and depending on which type of chemistry, isocyanate and polyol, you can have the foam that has open cells or closed cells, which means it's rigid, solid like wood, or flexible like the pillow or seats in your car. And those are all urethane. And the urethane industry, to make this idiot proof, came up with something called an A and B side. I should warn you, I have 6 or 7 patents in urethane foam technology, so I know this side. Now, you have an A side, and that's the isocyanate. Why did it change color on me? It's not even Friday the 13th yet. Stop doing that. And the B side has your polyol, that's your alcohol, but to make a foam, there are other things. First of all, you need a catalyst, and you should know this, and that's the tertiary amine. Remember when we made polycat 8, I showed you? That's the key. Then you'll have a blowing agent. That's a very volatile, low boiling liquid or material. It used to be Freon. When I worked with this, was Freon until they found out what it was doing to our atmosphere, and now they use other chemicals. Then you have a silicone surfactant. To help make the foam better. And my patents deal with non-silicone surfactants to help make certain types of polyurethane foam. Now, when you mix, the way they have it set up, you have an A side and B side, and you mix equal amounts of each together. And they made it idiot proof for people out, and I'd say if you're insulating somebody's house. Now, how many of you have ever seen an old refrigerator from the 1950s? How thick is the walls? Very thick. Why? Because back then, in order to insulate the inner cold box to the outside, they used glass wool, which you need a lot to get an R value that will insulate it. Now, if you go in your kitchen now, or a friend's kitchen, if you look at your parents' kitchen, if you look at your refrigerator now, how thick are the walls? Like this. Why? Because it's now insulated with a rigid urethane foam. And therefore, urethane foams, you have a better R factor and you need less. Now, if you're sitting on a chair with a nice cushion, as opposed to sitting on a piece of wood or metal, you're sitting on one with open cells, which is called flexible foam. Now, we were in the lab a couple of years ago at a company. I got the flexible foam formed A and B sides, stopped selling it, so we could only do the rigid one. Ooh, I usually don't bring it in. Hold on. If you work in urethane foams, a badge of honor is to create the following. This is a rigid urethane foam. You make it in a cup like this. And if you get the catalyst right, you pour it and it hardens just like this. It took me only 3 tries to do this. God, I forgot how many years old this is. Needs a good dusting. Hold on. But anyways, this is one of my prized mementos of days when I made urethane foams. And isn't that cool? And you can just hold it like this and look, oh, it's standing by itself. But anyways, what you do is you mix the A and B side together, mix it real quick. In the lab, you just use a tongue depressor. When I did research for that, and I had to make foams do various testing, various parameter, I had a very special high-speed air motor that went at about 300 RPM. More than that, 500 revolutions per minute. It was quick. It had a special mixing head that did not incorporate any air. That mixing head blade cost about $500. But it was worth the research. We needed it. And so the company bought it. All right, now, when you mix things together, the first thing you're going to see is the isocyanate. If you're making a rigid foam, it's called polymer. It's a brown color. Your polyols looks like honey. When you mix together and the reaction starts, you'll see it turn that color like the foam, a cream color. And what I mean by a cream color is it looks like if you had black coffee, you added cream to it. It lightens up. So the chemical industry or urethane industry has a measurement called the cream time. And that's when the reaction starts. And that's an important number to know. If you're pouring something into a mold, you want a slower cream time. Now, the lower the cream time, the faster the reaction. And how can you adjust that? By how much catalyst you add. Now, when you've made the foam, while it's still rising or curing, it's sticky. And a good thing to know is called the tack-free time. And hopefully I'm spelling sticky and tacky right. And you take a tongue depressor, touch it after a couple of minutes to the top of the foam. And if it pulls away without pulling anything with it, it's no longer sticky. Sort of like if you had something like Scotch tape or masking tape, this would stick to it. When it no longer sticks, It's tack-free. Now, if you were in the lab, you'd be mixing an A and B part. It's a lot of fun. And guess what? You'd make a foam and then you'd measure the cream time by looking at the clock or counting 1001, 2. And then after a couple minutes, checking for tack-free time. I apologize. I don't know why this is giving me problems today. Hold on, let me try something. Hang in there, I'm closing some stuff, forcing it. All right, let's try this again. All right, let's try this again. All right, back to where we were. And here I show you the procedure. If you were in the lab, you'd weigh out 10 grams of the A side, 10 grams of the B, and you'd mix the two together and watch and have fun. Now, let's do this. I have a YouTube video for you to look at. Let's go to that real quick.
Today we were talking to start mixing that.
All right, notice he's got the dark B side with the A side. Can you all see it? You see it all? All right, now can you see it? Let's back up. And by the way, you can go look at this on your own. See here, A side and B side, he's just mixed. Let's go back a little. Here he's got the A and B side. See how they made it idiot proof? The dark one is the A side, the light one is the B side. Watch, see how it's dark? And as soon as he starts mixing it, cream time in about 3 seconds. Now, in real life in a lab, you have a much better stir, but for now, and we use tongue depressors as opposed to spatulas because students don't always get the urethane foam off quick enough and it's hard to get it off. Now, let's watch. Remember the B side has the blowing agent and everything? Is a slow rising. Now, this is an exothermic reaction. It gives off heat. Oh, look, it's alive. See how it's rising? in the lab, we don't put that much so it overflows like that. And it's forming a foam. If you notice, similar to the color I showed you mine. And now, after a while, see how he can touch it? It's solid. And that's a urethane foam. All right, let's continue on with the lab. By the way, if you were in the lab, you would measure. Everybody see the lab now? Thank you. You'd measure the cream time, tack-free time. Does it heat up? And the answer is yes. The heat from that is what causes the blowing agent to expand to make the foam. By the way, how many of you have ever made bread? Bread is really a foam that's hardened, just like a solid urethane foam, except one you eat and the other you don't. And the next one, we're going to be doing nylon. Now, nylon is a reaction. Now, here I have an acid chloride. Think of that as like a carboxylic acid, but more reactive. And react it with an amine, you form an amide. Now, if I have a acid chloride and a diamine, I'll form a polymer that has many amide linkages. And we call this nylon. And the original nylon had the acid chloride with 6 carbons in it and the diamine with 6 carbons. So it's called nylon 6,6. And in the lab, again, this is sad because you're not actually able to do this. Now, you have 2 layers. One where you have the acid chlorides and the other, the nylon, the diamine with the some base, because this gives off HCl, and you want that neutralized because amines react with HCl, and you don't want to make amine salts of your diamine because that chews it up. This is one of the labs where I enforce everybody has to wear gloves. And you'll notice he's going to very carefully pour the diamine solution into the acid chloride. By the way, that smoke is the acid chloride reacting with some of the moisture in the air. You notice there are 2 layers here, right here. And now in between where the layers touch, they react to form nylon, and he's going to pick it up. And see that white stuff? That's nylon. Now, the way I have it, he's using a spatula. I have students wrap it around the beaker. And usually you can spend about 5 minutes wrapping tons of nylon. See how he's keeping on? And the interface there is where the polyacid chloride and the polyamine react to form a polyamide. See how he's going on? You could do that for about 5 minutes. Like I said, I have you wrap it around a beaker. It's a lot more fun than the way he's doing it, even though he's having it. And you're making a polymer, and that's nylon. Now it's further treated to make the things that you're used to buying that are made of nylon. Example would be pantyhose. I don't know what leggings are made of. I think spandex and other polymers. But I'll let you watch this at your own leisure, and you can come back. The link is there. Now, one thing you should know, nylon is an amide. And you learned about amides, and you can have acid hydrolysis. And that's one reason why, if you have some nylon, you don't want acid on there. Now, the reason I thought of that, and I don't know if leggings are polyester, which also esters will acid hydrolyze, but a while back in one of the other labs, I had a student who wore leggings, got a little acid on her leggings. We took care of it with paper towels and water, so her skin wasn't injured, but within seconds, the fabric was gone because it broke down. Acid hydrolysis. Now, that's part 3. By the way, these are the different, here's the acid chloride, here's the diamine we use, 1,6-hexane, 1,6-diamine, and it's really cool to do. Unfortunately, I can't let you do that at home. Now, the last one, let's talk about the reaction of alcohols with boric acid, actually sodium borate. And this reaction, let's go back to the whiteboard. Going a little over than I planned, but I've got to open it up. All right, boric acid has this structure. And turns out if you react it with alcohols, everybody see my whiteboard? And this is called a borate ester. It's like a carboxylate ester, but it's a little different. So what's the effect of R on here? Now, one R group you're going to use is, I forgot which alcohol I have you use. Let's take a look. Is isopropyl alcohol. And you're going to take isopropyl alcohol Actually, it works better with sodium borate, but I'm not going to go into the chemistry. And you'll make a borate ester. I'm not going to show you because I'm going to let you figure it out. Now, the other one you're going to do is you're going to use Elmer's glue. Now, what's Elmer's glue? It's mainly polyvinyl alcohol. If we were at ECC, I'd be writing this on the board, and N is about 1,000,000, 10 to the 6th. This is a huge polymer. And notice there are a lot of hydroxyl groups, so the borate ester you make can be like this with a lot of cross-linking too between the different molecules. And these are very long. With this, you're not going to get any cross-linking. It's going to be small. Will that make a difference in water solubility? I'm not going to give it away. Well, sort of not. And this students love. And you're going to be making this stuff. We don't use food dye. And it has another name, monster slime. And depending on how much boric acid or sodium borate, you can do this at home with Elmer's glue and borax, 20-multene borax and water, and watch what happens. we already have these solutions made up in the lab, so you just mix the Elmer's glue with this. You don't use that much Elmer's glue, but enough to have fun. Now, there are variations of this where you use pure, not Elmer's glue, but you use a pure polyvinyl alcohol, which is clear. And that's how the movie makers get, like on Star Wars, that slime dripping from the mouth of the monster. It's this reaction. I bet you never thought that Hollywood uses chemistry, organic chemistry. And I don't have people use food dye. You can at home, but it's messy. Looks nice though on screen. Two days later, they're adding now I don't have you do it that slow. See how it's getting slimier? And you'd make that, and I go around and some of the students would go, oh, is this gross? And I'd say, it's monster slime. Dr. White, and you would have a nice time. And you'd observe if you, when you reacted the alcohol with boric acid, you get for isopropanol clear liquid, for polyvinyl alcohol, otherwise known as Elmer's glue, you get this gooey, slimy white solid, like you saw if it didn't have food coloring in it. And that's the lab. And here are the questions. With that, I'm done. I will be sending out in about 10, 15 minutes or less the email with the password for test number 3. You have until tomorrow about 10 or noon to get it uploaded with your answers. I hope by Sunday 1 p.m., but it'll probably be a lot sooner, I will have your grades in D2L. I'll send out an email and post an announcement. On Monday's lecture, I'll go through the whole test with answers, and I will remove that from the video. So if you can't make it there, come to my office hour, or if you can't do that, let me know, and I'll help you out. We'll set up some time if you need to see it. With that, we're done for today. And with that, I'll say, gang gesund, be healthy. I'll see you on Monday. Don't forget to do the test, and don't forget to hand the lab that's due today. And with that, I'll say goodbye.